in a laboratory somewhere in the world, in a room kept darker and stiller than the deepest part of any night, on a heavy table that floats to hush away every tremor, two small flecks of light are born in the very same instant, from the very same sliver of crystal, as though the universe had drawn a single breath and let it out in two directions at once. They leave together in the same breath of their making. One flies east, one flies west, and they keep flying at the full speed of light, growing farther and farther apart with every passing instant, until a whole city lies between them, then a country, then the gentle curve of the earth itself, and farther still. And here is the thing that has unsettled and delighted the cleverest minds of the last 100 years, the gentle riddle that lies at the centre of this whole long night. Those two flecks of light, no matter how far they wander, no matter how much cold and empty space comes to lie between them, still behave as though they are, in some deep and quiet way, a single thing. Look closely at one, and the other answers in the same heartbeat, across any distance, as if the space between them were only a rumour, and the truth were that they had never truly been parted at all. Whether a hand's width lies between them, or the whole breadth of a continent, the answer comes just the same, with no delay anyone has ever been able to measure. It is as though the two flecks of light have quietly agreed to remain, in some deep way, a single thing, no matter how the world tries to pull them apart. You do not need to understand any of this tonight. You do not need to hold the numbers, or follow the argument, or keep awake to catch the ending. Let the mind go loose and warm. Let these ideas move through you the way light moves through dark water, touching everything, gripping nothing. Some of it will stay with you by morning, settled somewhere soft and dim, and most of it will simply have passed through, and that is exactly as it should be. There is nothing here to solve. There are no questions on the far side of this, no test in the morning, no need to carry a single fact past the threshold of sleep. There is only a quiet wonder to rest inside, the gentle astonishment that the world, all the way down at its smallest grain, is woven together more closely and more tenderly than anyone ever guessed. So loosen your shoulders, let your jaw unclench and your hands fall open. Let the breath find its own slow rhythm, and let yourself be carried, without effort, without doing anything at all, into the strange and beautiful country of the very small, where two things separated by half a world can still, in some deep and gentle sense, be one. The word for it is entanglement, and it is one of the most carefully tested truths in all of science, though it sounds at first like something out of a dream. Picture two coins that were minted together, sealed in two envelopes, and carried off to opposite ends of the galaxy. In the ordinary world, each coin is already heads or tails from the moment it was sealed, hidden but fully decided, waiting only for someone to look and reveal what was true all along. The quantum world is stranger and softer than that, and far less settled. Until someone opens an envelope, neither coin is chosen, neither is heads nor tails nor anything definite at all. They hang together in a haze of every possibility at once, undecided in a way nothing in ordinary life can match. And the moment one is opened and found to be heads, the other, light years away, settles instantly into tails, not because a signal raced between them through the dark, not because the first coin sent word to the second, but because they were never two separate stories. They were always a single story, told in two places. That single shared description, that one connected state spread across the gap, is what physicists mean by an entangled pair. Neither coin owns its own answer. The answer lives only in the pair, in the relationship between them, and reveals itself only when one is looked at and the other compared. Learning to make these pairs, and hold them, and read them without breaking them, has quietly become one of the great adventures of our age, a patient century-long labour reaching from a puzzle on paper all the way to machines that cradle the connection in the palm of the world. It begins, as so many beautiful things do, with a disagreement, a friendly quarrel among brilliant minds about what the world is truly like underneath. In the year 1935, Albert Einstein, working with two younger colleagues named Boris Podolsky and Nathan Rosen, wrote a short and now famous paper meant to expose what they felt was a flaw at the very heart of the new physics, a paper that has been read and argued over ever since. Surely, they argued, two particles cannot influence each other across a great distance in no time at all. Surely the world could not be so unreasonable. Each particle, they insisted, must carry its answer already inside it, written and waiting from the start, the way the sealed coin carries its hidden face beneath the paper. Einstein gave the troubling idea a name that has clung to it ever since, half in suspicion and half in awe. He called it spooky action at a distance. He hoped the spookiness would prove that the theory was incomplete, that some quieter, more sensible explanation lay hidden underneath, waiting to be found. He was perhaps the greatest physicist who ever lived, and on this one question, by the lights of the evidence we now hold, he turned out to be mistaken, though his error was the kind that only a profound mind could make, and it set the stage for everything that followed. The wonderful, humbling turn in the story is that nature, when finally asked the question directly, in experiment after careful experiment, sided not with Einstein's comfort, but with the very spookiness he had hoped to banish. That same year, on the other side of the argument, the physicist Erwin Schrödinger read Einstein's paper and felt the ground shift beneath him. He saw at once that the strange linking of distant particles was not a small wrinkle to be smoothed away, but the very signature of the quantum world, the feature that set it apart from everything that had come before. He had read the paper and seen at once that it touched something far deeper than its authors intended. It was Schrödinger who gave the phenomenon its lasting name. In English he called it entanglement, and in his native German, Verschränkung, a word suggesting things folded and crossed over one another, like fingers laced together or arms crossed over a chest. He wrote that it was not one but rather the characteristic trait of the new physics, the one feature that forces a complete departure from all our classical ways of thinking. Curiously, the very same year, in the very same line of thought, he dreamed up his famous image of a cat whose fate is bound to a single tiny particle, the most haunting illustration ever made of how this strange linking could climb from the smallest scale toward the world we know. He had glimpsed, with something close to dread, just how deeply the tiniest pieces of the world could be bound to one another and to everything else. For nearly 30 years after that, entanglement lived in a curious twilight, neither embraced nor explained. It was real enough on paper, written plainly into the mathematics that every physicist used and trusted every working day, and yet there seemed to be no way at all to settle the deeper argument by experiment, no test anyone could imagine performing. Was Einstein right, that hidden instructions were tucked inside each particle from the start? Or was the world truly as strange as the equations implied, with no answer decided until the moment of looking? The question seemed to belong to philosophy rather than to the laboratory, a matter of taste and intuition that no measurement could ever decide. The mathematics worked perfectly either way, predicting every experiment with flawless accuracy, and so the deeper question of what lay beneath seemed not to matter for any practical purpose. Generations of brilliant people simply set it aside, used the theory to build transistors and lasers and the first computers, the very machinery of the modern world, and let the puzzle of what it all meant rest in the dark, unanswered and apparently unanswerable, a beautiful riddle that ambitious young scientists were quietly advised not to waste their careers upon. Then, in 1964, a soft-spoken Irish physicist named John Stuart Bell did something that changed everything, working quietly on the side while his main job lay elsewhere. By day, he designed particle accelerators at a great laboratory in Switzerland, and the question of entanglement was a private fascination he pursued in stolen hours, almost as a hobby. He found a way to turn the old philosophical quarrel, which had seemed forever beyond the reach of any experiment, into a sharp and answerable question, a question that real instruments in real rooms could one day decide. Bell saw that if Einstein was right, and each particle carried its hidden instructions from birth, then the results of many measurements on many pairs would have to obey a certain strict limit, a ceiling they could never cross. But if the quantum description was the true one, the particles would, in just the right kind of test, sail straight past that ceiling. The difference was no longer a feeling, it was a number you could measure. With a few lines of elegant reasoning, Bell had handed the universe away to speak for itself, and all that remained was to listen. What Bell proposed is now known as his theorem, and the limit he discovered is called a Bell inequality, though you need not remember the names, nor any of the names tonight, to feel the beauty of the idea. The names are only labels, the wonder beneath them needs no remembering at all. Imagine a fair coin-tossing game played by two people in distant rooms, far enough apart that they cannot signal one another, each free to choose, at the last possible instant, which of a few different questions to ask their particle. If the answers were fixed in advance, like the faces of those sealed coins, then over thousands of rounds the patterns of agreement between the two rooms could only rise so high and no higher. That ceiling is the inequality. It is a promise that any world built from hidden, local instructions must keep. And the whole astonishing point is that our world, when tested, does not keep it. The agreement between the rooms climbs higher than any hidden script could ever allow, and in that small excess lies the proof that the particles are doing something far stranger and more connected than common sense permits. There is even a precise mathematical edge to how far the agreement can climb, discovered by a mathematician named Cyrilson. The quantum world is strange, but it is not infinitely strange. It pushes past the classical ceiling by a definite, calculable amount and then stops, holding to a second, higher limit of its own. The universe could, in principle, be wilder still, more connected than the quantum rules allow. It is not. It sits exactly at the gentle edge that quantum mechanics marks out, neither tame nor unbounded, perfectly poised between the two. It took years to actually run the test, for the experiment is delicate almost beyond belief, requiring single photons to be made and steered and caught one at a time, and the first serious attempt came in the early 1970s from a young American named John Clauser, working at a laboratory in California. Working with little money and a great deal of patience, often building his own equipment by hand, he and a colleague assembled an apparatus that fired entangled photons toward detectors on either side and counted one by one, over many long hours, how often their answers matched. He was, by his own later account, half hoping to prove Einstein right and overturn the strange new orthodoxy to find the comfortable hidden instructions everyone of good sense expected. Instead, his careful counts came down clearly on the side of the spookiness. The particles broke Bell's ceiling. The hidden instructions were not there, had never been there. It was the first time a human being had watched the deepest weirdness of the quantum world reveal itself, not in theory, not in argument, but in the steady accumulation of real clicks from a real machine in a real room, the universe answering a direct question with a plain and startling yes. Sometimes the world declines to be as sensible as we wish, and tells us so in numbers we cannot argue with. Still, a good experiment always invites good objections, and that is how science sharpens itself. The early tests left small gaps a determined skeptic could still slip through, loopholes with names like locality and detection, narrow doors through which an ordinary explanation might yet escape. Perhaps, some said, the two sides of the apparatus were quietly influencing each other after all, through some signal no one had noticed. In the early 1980s, a French physicist named Alain Aspect set out to close that particular door with great ingenuity and even greater patience. He arranged for the choice of what to measure to be made so quickly, switched at the very last instant as the photons were already in flight, that no signal travelling at the speed of light could possibly have carried word from one side of the apparatus to the other in the brief moment that remained. If the two sides were somehow coordinating in secret, that coordination would have had to outrun light, the one thing the universe forbids. And still the strange agreement held. Even when the two detectors could not have whispered to each other by any ordinary means, the entangled photons answered as one. Each closed loophole only deepened the wonder, narrowing the room until there was nowhere left for the old comfort to hide. With every refinement, the experimenters were not trying to prove the spookiness true so much as trying their hardest to prove it false, hunting for any ordinary explanation that might still slip through. That they kept failing decade after decade is the strongest sign of all that the strangeness is simply real, as much a part of the world as gravity or light. For decades the work went on like this, each generation of physicists building cleaner experiments than the last, closing one small gap after another, sharpening the question with every passing year, until at last in the year 2015, 3 separate teams in 3 separate countries did something that had once seemed impossible. They closed all the major loopholes at the same time in a single carefully designed experiment, leaving no ordinary explanation standing anywhere in the room. One of those teams worked in the Dutch city of Delft, and their setup is worth resting your imagination upon, for there is a strange beauty in how they did it. They took 2 tiny diamonds, each holding a single flaw deep in its crystal, where one carbon atom was missing from the otherwise perfect lattice, and within each of those flaws lived a single trapped electron, held like a small captive spark. The 2 diamonds sat in separate laboratories more than a kilometre apart, about 1 1/3 kilometres across the campus, and through a thread of glass the electrons were coaxed into a shared, entangled state. The distance was chosen with great cunning, far enough that no signal moving at the speed of light could cross from one diamond to the other during the brief instant of the measurement, sealing shut the door through which a hidden influence might have slipped. Then, again and again, the scientists asked their distant questions, and again the answers agreed beyond the limit that any hidden script could allow. Within the same few months, 2 more teams, one in Vienna and one in the high air of Colorado, reached the very same verdict by their own separate roads. The result was as clean and quiet as a held breath, and it settled the oldest argument in quantum physics about as completely as nature ever settles anything. For this long patient labour, stretched across half a century, the highest honour in science finally arrived. In 2022, the Nobel Prize in Physics was given to 3 of the people who had made entanglement real to us: John Clauser for the first daring tests, Alan Aspect for slamming shut the loopholes, and the Austrian physicist Anton Zeilinger for showing how this strange connection could be put to work. The award was given, in the committee's own words, for experiments with entangled photons that established the violation of the Bell inequalities and opened the door to quantum information science. 3 people, working in different countries across different decades, often without ever sharing a room, each adding a careful stone to the same patient structure, until together they had built something wholly undeniable. None of them could have finished it alone, and yet between them the thing was done. It was in a sense an apology and a tribute at once, a recognition that the spookiness Einstein hoped to banish had turned out to be one of the truest and most useful features of the world. A decade earlier, in 2012, the prize had already gone to 2 other pioneers, Serge Haroche and David Wineland, who had each found ways to gently measure single particles of light and matter without destroying their fragile quantum states, laying some of the groundwork on which all this rests. The dreamlike thing, once dismissed as idle philosophy, had become the foundation of a new kind of technology, honoured at the very summit of science. Now here is the gentlest and most reassuring part of the whole story, the part that lets you rest easy inside the wonder. Although the link between entangled particles seems to leap across any distance in no time at all, it cannot be used to send a single message faster than light. Nothing about the cosmic speed limit is broken, and nothing ever races ahead of a beam of light to carry news. The reason is subtle and lovely, and worth holding gently in the mind. When you measure your half of an entangled pair, the result you get looks completely random, an even scatter of outcomes with no pattern at all, no message, no meaning anyone could read. Your distant partner, measuring their half, sees the very same featureless randomness, an equally meaningless string of results. Only later, when the 2 of you bring your lists of results together and lay them side by side, does the hidden harmony appear, the perfect matching that was there all along. Apart, each list is meaningless noise. Together they reveal the connection, and so the secret keeps itself, and the universe stays exactly as orderly as Einstein wished, even while being far stranger than he hoped. Sink a little deeper into that thought, for there is real and lasting comfort in it, the kind worth carrying down towards sleep. The strangeness of entanglement is not a crack in the world through which chaos might one day pour. It is a calm, lawful, beautifully behaved part of reality that breaks no rule and threatens nothing. The randomness you would see in your own measurements is a perfect veil, ensuring that no one can ever exploit the connection to outrun light or unravel cause and effect. Imagine trying to send a message this way, straining to force your particle to spell out words. You would find only an even, meaningless scatter, no matter what you did, the harmony revealing itself solely in the later comparing. The cosmos guards its own consistency with great and tireless care, allowing the wonder while forbidding the paradox. The wonder and the order live together, hand in hand, two halves of a single truth, and there is nothing here to fear, only something marvellous to rest within as the body grows heavier and the room grows dim around you. You may let go of any worry that the world is somehow unsafe at its foundations. It is not. It is stranger than the old picture, yes, but no less steady, no less lawful, no less gently dependable than it has ever been beneath your feet. The particles most often chosen for these experiments are photons, the tiniest possible pieces of light, and one of their hidden qualities is something called polarization, the direction in which the light's wave is leaning as it travels. Picture a single ray quivering up and down, or side to side, or at any slant between, like a jump rope shaken in some particular plane. In an entangled pair, neither photon has a settled lean of its own until it is measured, each one a soft blur of every possible angle at once. Yet whichever way one is found to be leaning, its partner is found to lean in a perfectly matched way, instantly, however far apart they have flown. This is the property the experiments watch most closely, because polarization is easy to test, with nothing more than the right kind of crystal or filter, the same physics that dims the glare in a pair of polarized sunglasses. A photon arriving at such a filter either passes or is absorbed, and when two photons are entangled, the pattern of which ones pass on each side reveals the hidden harmony between them. From this simple leaning of light, measured millions upon millions of times, comes nearly all the hard knowledge there is about how entanglement truly behaves. It is a humbling thought that so much understanding of the deepest connection in nature rests upon something as gentle as the way a sliver of light chooses to tilt. To make these linked pairs of light, scientists often use a small slab of special crystal, sometimes barium borate or a relative of it, and shine a violet or ultraviolet laser into it, in a process with the grand name of spontaneous parametric down conversion. Most of the laser light passes straight through, untouched, as if nothing at all were there to meet it, emerging on the far side just as it entered. But once in a great while, perhaps one photon in many billions, a single incoming photon splits inside the crystal into two photons of lower energy, dividing its energy neatly between the pair, and those two emerge already entangled, born twinned and bound, leaning in matched and opposite ways. The pairs spray out along two faint cones of light, and where those cones cross, the photons are so thoroughly bound that neither holds a polarization of its own until one is measured. The crystal is doing nothing violent, nothing loud. It simply offers a quiet place where one particle of light can become two that remember each other. Out of that hush comes a steady trickle of entangled pairs, each one a tiny, perfect demonstration of the deepest connection in physics, ready to be sent down a fibre or out through the open air. It is not only light that can be entangled. The same shared state can bind electrons, the faint particles that swarm in clouds around every atom, and it can bind whole atoms together, and even the heavier nuclei buried at their cores, the dense little hearts of matter itself. Physicists have entangled the vibrations of tiny drum-like membranes and clouds of thousands of atoms chilled to within a whisper of absolute zero, and pairs of ions hovering in electric traps like motes held in invisible hands of pure force. They have entangled particles of different kinds with one another, a photon of light bound to the spin of an atom, the most fleeting of things tied to the most solid, as though the connection cared nothing for the deep differences between them. The link does not care what kind of thing it joins, only that the joining is done with enough care and enough stillness. Wherever the quantum rules hold, which is to say everywhere, entanglement is possible, a thread that can be tied between almost any two pieces of the material world, if only the world is kept quiet enough to let the thread hold, and the link can stretch astonishingly far. In a truly remarkable demonstration, one that earlier scientists could scarcely have dreamed of, a Chinese team led by the physicist Jianwei Pan sent entangled photons from a satellite orbiting hundreds of kilometers overhead down to two observatories on the ground, observatories separated from each other by more than 1,000 kilometers of mountain and open sky. The satellite, fittingly, was named Mitius, after an ancient Chinese philosopher who studied light and vision more than 2,000 years ago. Launched in 2016, it circled the Earth a few hundred kilometers up, sweeping overhead at thousands of kilometers an hour, and in its brief passes it became a fountain of entangled light, raining matched pairs down through the thin upper air to telescopes far below. The two receiving observatories sat among high mountains, in places named Delinga and Lijiang, more than 1,200 kilometers apart, farther than the length of many countries, and even across that vast separation the connection survived intact, sending the fragile photons up through hundreds of kilometers of open air, much of it thin and clear above the weather, turned out to lose far fewer of them than threading the same distance through glass fibre at ground level, where the light would have been swallowed long before arriving. It was the first time entanglement had been shared on such a scale, reaching from space all the way down to the surface of a planet, smashing the earlier earthbound records that had struggled to reach even 100 kilometers through fibre and air, and proving once and for all that this most delicate of bonds can be carried across the heavens themselves, from orbit to the patient telescopes waiting in the dark below, two threads of light falling like the gentlest of rain. That same satellite did something that would have astonished the founders of the field. It allowed two distant cities to share a secret key for encoding messages, a long string of numbers known only to them and to no one else anywhere in the world, with its security guaranteed not by human cleverness, which another human might outwit, but by the unyielding laws of physics themselves. Because any eavesdropper trying to intercept the entangled photons would inevitably disturb them, and that disturbance would show up in the results like a footprint in fresh snow. The two parties can always tell whether their key is truly private. Using this very method, researchers in China held a secure video conversation with colleagues far away in Austria, half a world away across the whole breadth of the continent, their words wrapped in a code that the deepest mathematics says can never be quietly broken by anyone. The two groups were separated by some 7,000 kilometers on nearly opposite sides of the turning planet, and the key that locked their conversation away from every prying ear was woven from light that had fallen, photon by photon, from a satellite passing silently overhead. It was a true milestone in the long history of human communication, the first time a secret had been kept not by the cleverness of a cipher, which a patient enemy might one day crack, but by the unbreakable laws of physics themselves, a privacy no future machine could ever undo. From a philosophical puzzle about coins sealed in envelopes had come, within a single lifetime, a way to keep a secret perfectly safe across the whole width of the world. There is a strict and rather poetic rule that governs how entanglement may be shared among many things at once, known by the tender name of the monogamy of entanglement. It says that the more completely two particles are entangled with each other, the less either of them can be entangled with anything else, as if each particle had only so much of itself to give away, and a fully given bond left nothing for any third. A pair bound together as tightly as the rules allow has, in a sense, given itself entirely to that one connection, with nothing left over to offer a third party. There is a tender image hidden in the name, of a faithfulness woven into the very mathematics of the world, a connection that cannot be divided among many without growing thin. This is no mere curiosity. It is the very reason quantum secrets stay safe, for it means an eavesdropper can never copy the connection without weakening it, never quietly insert themselves into a perfectly entangled pair. To listen in would require sharing the bond, and the bond, once fully given, has no more of itself to share. The intruder would find only a frayed and weakened thread, its telltale fraying a clear signal that someone had tried. The deepest bonds in the quantum world are faithful ones, exclusive by their very nature, giving themselves wholly to a single partner, and from that quiet faithfulness flows a kind of security the ordinary world can only envy. It is a strange and lovely thought that the safest secrets ever kept rest in the end upon a kind of devotion written into the smallest things there are. One of the most wondrous tricks built upon this connection carries a name borrowed from science fiction, though the reality is humbler and stranger than any story. It is called quantum teleportation, and it does not move matter from one place to another. No bodies dissolving and reappearing, no objects beamed across a room, nothing of the kind the old stories imagined. What it moves is a state, the complete quantum description of one particle, every detail of how it leans and spins and waits, transferred onto a distant particle so perfectly that the faraway particle becomes, in every measurable way, indistinguishable from the original. The first particle loses its state in the process, as if the information had been lifted clean off it and set down elsewhere. Nothing physical crosses the gap. Only the pattern travels, riding partly on an entangled link and partly on an ordinary message sent no faster than light. The first time anyone managed this in a laboratory was in 1997, when a team in the Austrian city of Innsbruck teleported the polarization of one photon onto another across their optical bench. Among the young researchers on that work was a student named Jan Wei Pan, the very same person who, 2 decades later, would build the satellite that carried entanglement down from space. The original is not copied but relocated, and the rules of the quantum world are kept whole and unbroken throughout. To picture how teleportation works, imagine 3 particles in a careful dance, each with its part to play. 2 of them, far apart, are entangled with each other, a prepared and waiting bridge laid down ahead of time, one end with you and one end with your distant friend. The third particle, the one carrying the precious state you wish to send, is brought together with your end of that bridge and gently measured in a way that scrambles the 2 of them together, blending the message particle with your half of the bond. The result of that measurement is a small handful of ordinary bits, just 2 of them in the simplest case, a tiny message no stranger than a pair of yes or no answers, which you then send to the distant end by any normal means, a phone line, a radio wave, a beam of light through the open air. Armed with those few bits, your distant partner makes one final adjustment to their waiting particle, a small turn chosen by the message they received, and in that instant it snaps into the exact state the third particle once held. Without those bits, the adjustment could not be made, and the distant particle would remain a meaningless blur. This is why nothing arrives faster than the ordinary message allows. The entanglement is used up in the doing, spent like a struck match that cannot be struck again, consumed to power the crossing, but the state has crossed the distance intact, lifted from here and set down there, whole and unchanged. No law of physics has been bent even slightly, and yet something that feels very much like magic has quietly taken place. This is the strict and elegant catch that keeps everything honest. Teleportation always requires that ordinary message, those few plain bits sent at light speed or slower, before the distant particle can be brought to completion. Without them, the faraway end holds only meaningless randomness, a particle in no particular state at all. The entangled link alone, for all its mystery, can never finish the job by itself, can never deliver the state without that plain companion message trailing along at the speed of light. And so once again the cosmic speed limit stands untouched, guarded by the very structure of the trick, built into its bones so deeply that it could not be otherwise. The wonder of teleportation and the lawfulness of the universe turn out to be the same thing seen from two sides, a connection that feels like magic, yet obeys every rule with perfect, calm discipline. The more closely you look at how it works, the clearer it becomes that the strangeness and the orderliness are not intention at all, but are woven from a single thread. There is a deep reason why a quantum state cannot simply be copied, a reason with a name as plain as a closed door. It is called the no-cloning theorem, and it says that there is no way, none at all, to make an exact duplicate of an unknown quantum state. You cannot scan a mysterious particle and print a perfect twin, cannot make a backup, cannot run off a second copy to keep in reserve. The act of looking always changes what you're looking at, gathering one answer and erasing the rest, and so the original can be moved, as in teleportation, but never simply photocopied while left intact. This single rule, proven in a few short lines of mathematics, shapes the whole landscape of what is possible in the quantum world, drawing the line between the tricks that can be done and the ones that never can. This sounds at first like a limitation, a thing the universe forbids. Yet it is also a kind of protection, the very rule that makes quantum secrets unbreakable. For if no one can copy a quantum message without spoiling it, then no one can listen in without leaving a trace. The world's refusal to be copied is the same as its gift of privacy. It is the deep reason that teleportation must destroy the original as it goes, for if the state could be both sent and kept, you would have made a copy, and that the rules will not allow. The information is not duplicated, but moved, lifted from one place and set down in another, the first place left empty. There is a strange honesty in a universe that will let you carry a secret anywhere, but never let you hold two of it at once. All of this connection and computation rests on an even stranger foundation, the quality the quantum world has that the everyday world lacks, called superposition. Before it is measured, a single quantum particle does not sit in one definite state, but hovers across many at once, a blend of possibilities held in delicate balance. A photon leans every which way until asked. A particle's spin points in no single direction until measured. This is not a matter of our ignorance, not a fact merely hidden from us, but a genuine in-between state with no counterpart in ordinary life, as real and definite in its own way as any single answer. Entanglement is what happens when two of these hovering, undecided particles have their possibilities braided together, so that the blur of one is tied to the blur of the other. Neither particle is undecided on its own anymore. Their two uncertainties have become a single shared uncertainty, woven together into one. Without superposition, there could be no entanglement at all. The connection is built from uncertainty itself, from the soft refusal of small things to commit to a single answer until the universe insists. When physicists try to capture this in the language of quantum computing, they speak of qubits, the quantum cousins of the ordinary bits inside any everyday machine. A familiar bit is always a firm 0 or a firm 1, a switch fully off or fully on, the simple alphabet from which every ordinary computer builds its whole world. A qubit, before it is read, can be both at once, leaning towards 0 and 1 together in a balance you can tune, holding a whole spectrum of in-between where the old bit knew only 2 corners. And when many qubits are entangled, their possibilities multiply in a way that grows almost dizzyingly fast, far faster than ordinary numbers can keep up with. Just a few hundred entangled qubits could, in principle, hold more distinct possibilities than there are atoms in the observable universe. The entire promise of quantum computing rests on weaving these qubits together and guiding their joined possibilities toward an answer no ordinary machine could reach. The trick, and it is an immensely subtle one, is that the answer must be coaxed to emerge while the wrong possibilities quietly cancel each other away, like ripples on a pond meeting crest to trough and falling still. A quantum computer does not simply try every path at once and read them all, for the act of looking would collapse the blur to a single random answer. Instead, it must be choreographed so that the paths interfere, the unwanted ones erasing one another, the right one left standing clear. Entanglement is what binds those countless paths into a single interfering whole. It helps to feel the scale of that promise, gently, without straining toward the numbers. Add a single qubit to an entangled set, and the space of possibilities does not merely grow, it doubles. 10 qubits hold over 1,000 combinations at once. 20 hold more than 1,000,000. 60 entangled qubits would hold more possibilities than there are seconds since the universe began, and 300 would hold more than there are atoms in all the visible heavens. This is why a working quantum computer could, for certain special problems, finding the factors of an enormous number, modelling the dance of molecules, do in a moment what would take an ordinary machine longer than the age of the cosmos. The power comes not from speed in any familiar sense, not from doing the same steps faster, but from this branching, blossoming richness that entanglement unlocks, a garden of parallel possibilities tended all at once. It is less like a faster runner than like a different kind of space to run in, wider than anything the ordinary world can offer. Such machines are real, though still young and easily startled, prone to losing their fragile states at the faintest disturbance, and the largest of them now hold not just a handful but hundreds of qubits, with the leading machines pressing past 1,000, knit together with entanglement and chilled almost to the absolute bottom of cold. They live inside elaborate golden chandeliers of wire and tubing, hanging in sealed chambers colder than the empty space between the stars, far colder than the surface of any planet. The deep space between galaxies hovers a few degrees above the lowest possible cold, warmed faintly by the afterglow of the universe's birth. Yet these machines are chilled colder still, down to 1/100th of a degree above absolute zero, the coldest temperatures anywhere in the known cosmos, made by human hands in quiet rooms. The cold is not for comfort but for stillness, for at such temperatures the restless jostling of ordinary heat, the endless trembling that warmth always brings, falls almost entirely silent, and the fragile entangled states can hold together a little longer before the world reaches in and disturbs them. Warmth, for all its kindness in ordinary life, is the great enemy of the quantum, and so these machines are built around a heart of profound and deliberate cold. To look upon one of these machines is to see a strange and beautiful cathedral built for a single purpose, to keep the quantum connection alive in a universe that is forever trying to break it. And break it the universe does, constantly and without malice, through a process called decoherence. An entangled state is a private conversation between particles, and the moment the noisy outside world overhears even a whisper of it, the conversation collapses into ordinary disconnected fact. A stray photon, a faint vibration, a breath of warmth, any contact at all with the surrounding world can sever the link in a fraction of a second, often in less time than light takes to cross a single room. This is the great reason entanglement feels so absent from everyday life, while your coffee cup and your spoon are not mysteriously bound. It is not that the rules change as things grow larger. The same quantum laws hold all the way up, from a single electron to a mountain to a star. It is that larger, warmer things are forever touching their surroundings, leaking their quantum secrets into the air and the light around them faster than any eye could follow, their delicate connections smeared away into the world almost before they form. The world is simply too warm, too busy, too full of small collisions for the fine threads to survive in the open. The strangeness is not absent from your everyday life. It is merely hidden, dissolved into the steady solidity of ordinary things. Entanglement is everywhere possible, and almost nowhere lasting, a fragile grace that the ordinary world rubs away, almost as fast as it forms. There is something strangely comforting in that fragility, if you let yourself feel it. The reason your waking life seems so solid and separate, each object sitting plainly in its own place, is that the warmth and motion all around you are forever smoothing the quantum strangeness away, leaving behind the steady, dependable world your senses know. Decoherence is the quiet hand that turns the shimmering blur of possibility into the firm, single reality you live inside. Far from being a flaw, it is the very thing that makes the ordinary world ordinary, the bridge between the dreamlike rules of the very small and the calm, definite room in which you are now resting. Without it, the world would be an endless smear of overlapping maybes, and there could be no single solid moment to live inside at all. It is the reason the walls stay where they are, the reason the floor holds firm beneath you, the reason each thing is simply itself and nowhere else. The strangeness has not gone anywhere. It has only been gently hushed, all around you, all the time, pressed down into the firm and familiar shapes your senses have always trusted. Among the properties most often entangled is one called spin, a quality every electron carries, though the name can mislead. The electron is not truly whirling like a tiny planet, for it has no size to spin and no surface to turn. Spin is something deeper and more abstract, a kind of intrinsic magnetic leaning woven into the particle's very nature, a property as fundamental as its mass or its charge, that can point one of two ways, often called up and down, when it is finally measured. The name is a charming accident of history, a word borrowed from the spinning tops of the ordinary world to label something that has no true counterpart there at all. In an entangled pair, the two spins are perfectly opposed, like two dancers turned forever back to back, so that if one electron is found pointing up, its partner is found pointing down, instantly and without fail, no matter the distance between them. Yet before the measurement, neither electron points anywhere at all. The opposition exists only as a promise held between them, a balance kept in waiting, until the act of looking calls both answers into being at once. Stranger still, the matching holds no matter which direction the scientists choose to measure along, up and down, left and right, or any tilt between, a choice they may make freely at the last instant. Whichever axis is picked, the two electrons are always found to disagree along it, perfectly, every time. No set of hidden labels written in advance could ever satisfy every possible question at once, and it is exactly this impossibility that Bell turned into his famous test. The connection need not bind only two particles. Three or more can share a single entangled state, woven together in arrangements with names like the GHZ state, after the three physicists who first described it. In such a trio, the three particles share one fate so completely that measuring any one of them instantly fixes the others, and the patterns they reveal violate the old hidden variable picture even more sharply than a simple pair. There is a strange totality to these many particle states, a sense in which they cannot be taken apart into separate stories at all. The whole is genuinely more than the sum of its pieces, bound into a single quantum object that happens to be spread across several particles, each one holding no private truth of its own. The three physicists who first wrote down such a state, whose initials give it its name, showed that a trio of entangled particles can defy the old hidden variable picture, not just on average, across many trials, but in a single sharp prediction that classical reasoning gets exactly backward. Where a simple pair reveals its strangeness gradually, through patient counting, a trio can betray it in one decisive stroke. The more particles are woven together, the more completely the connection refuses to be explained away by anything hidden inside the separate pieces. One of the most beautiful tricks in the whole field lets entanglement be passed along like a flame from candle to candle, even between particles that have never met. It is called entanglement swapping, and it works like this. Take two separate entangled pairs, 4 particles in all. Bring one particle from each pair together and measure them jointly in just the right scrambling way, and something remarkable happens. The 2 particles you did not touch, the lonely ends of each pair become entangled with each other, despite never having shared the same place or moment, despite being, in every ordinary sense, perfect strangers. The connection has leapt across the gap, handed off through a measurement, conjured between two things that never met. Picture a chain of these handoffs laid out across a landscape, each link short enough to survive, the entanglement passed along from station to station like a baton in a relay, until the two far ends are bound though oceans lie between them. This is how entanglement might one day be stretched across continents, relayed from link to link, a bond between strangers built entirely from other bonds. It is a strange kind of inheritance, a connection that need never have been forged directly, arising instead from the careful joining of connections that came before. That relaying idea points toward a grand dream that scientists are slowly building, a quantum internet. The trouble with sending entangled photons through long fibers of glass is that the glass slowly absorbs them, so that over hundreds of kilometers the precious pairs are lost into the dark. An ordinary signal can simply be amplified along the way, but a quantum signal cannot be copied by that same no-cloning rule, and so it cannot be boosted in the usual fashion. The answer lies in devices called quantum repeaters, which use entanglement swapping to hand the connection along in shorter, survivable hops, refreshing the link at each station so that no single stretch is ever too long to cross. Each repeater stores its fragile piece of the bond in a small quantum memory, waiting until its neighbours are ready, then passing the connection onward, like a relay runner handing off a baton. The technology is still young, the memory's still hard to hold, but the path is clear. Stitch enough of these together, and entanglement could one day span the whole globe, a web of perfectly private connection laid quietly beneath the ordinary internet of light and wire, a second and deeper network humming softly within the first. The same connection that powers computers and codes can also sharpen the human sense of time itself. The most precise clocks ever built are atomic clocks, which keep time not by any swinging pendulum or ticking gear, but by the steady inner vibration of atoms, a rhythm so reliable that it now defines the very length of a second for the whole world. Physicists have learned that entangling those atoms can make such clocks finer still. When the atoms share a single entangled state, their tiny ticks line up in a way that beats down the natural jitter, letting the clock measure the passage of time more exactly than any unentangled clock could manage. The finest of these clocks are already so accurate that they would neither gain nor lose a single second across the entire age of the universe, 14 billion years and more. They are so sensitive that lifting one a few inches higher off the ground changes its rate by a sliver, because time itself runs very slightly faster the farther you rise from the Earth, just as Einstein foretold. Entanglement, that dreamlike thread, turns out to be a tool for the most practical thing imaginable, for telling time with a steadiness the cosmos itself can barely trouble. This sharpening reaches into the realm of sensing too, in a field called quantum metrology. Because entangled particles share a single state, a set of them can be used to measure faint signals, a whisper of magnetism, a trembling of gravity, a flicker of rotation, far more keenly than the same number of separate particles ever could. The entanglement lets their answers add together in a way that cancels out much of the random noise that would otherwise blur the result. Scientists are using this to build sensors of astonishing delicacy, instruments that might one day map the hidden structure of the brain by its faint magnetic fields billions of times weaker than the one that turns a compass needle, or feel the subtle tug of buried caverns and pipelines deep underground by the faint dimple they leave in the local pull of gravity. There are entangled sensors fine enough to register the passing of a single distant footstep as a tremor, or to detect a magnetic whisper 100 million times fainter than the Earth's own field. The strangeness of the very small becomes, in these hands, a way of perceiving the world more gently and more truly, of feeling what was always there, but always just beneath the threshold of noticing. Even the great gravitational wave detectors, the vast instruments that listen for ripples in space itself, have been quieted by a clever use of quantum trickery closely related to entanglement. these detectors are limited by a faint, irreducible fuzziness in light, a quantum jitter that no amount of engineering could simply switch off. By preparing the light in a specially correlated state, a cousin of entanglement called a squeezed state, physicists have learned to push that jitter out of the measurement they care about and into a measurement they can ignore. The result is a detector that can hear fainter cosmic whispers than the raw laws of light would seem to allow, sensing motions thousands of times smaller than the nucleus of an atom. The most delicate listening humans have ever done, straining to catch the faint chime of two black holes colliding a billion years gone, their tremor arriving here as the gentlest shiver in a beam of light, has been made keener by mastering the soft rules of the quantum world. It is a marvel upon a marvel that the same physics which binds two particles should also help in overhearing the deepest events in the cosmos, the faraway folding of space brought within reach by the careful taming of light's own restlessness. It is worth resting for a moment on just how perfectly random a single quantum measurement is, for this too is a kind of marvel. When you measure one half of an entangled pair, the particular answer you receive, up or down, this lean or that, is not merely unpredictable in practice the way a tumbling die is. It is unpredictable in principle, as deeply and truly random as anything can be, with no hidden cause beneath it that a cleverer observer might uncover. The universe, at its smallest scale, genuinely flips a coin, and not even the universe knows the outcome in advance. This is not a gap in our knowledge waiting to be filled by some cleverer theory. It is, as far as the most careful test can tell, the bare and final truth of how things are. From this bedrock randomness, physicists now build the purest random numbers in existence, drawn straight from the bottom of reality, untouched by any pattern, for use in security and science. There is a strange peace in that thought, that some things are simply, cleanly, beautifully undecided until the very moment they happen, that the next outcome is not lying in wait somewhere, already fixed, but is genuinely open until it arrives. The future, at least down here, is not yet written. These pure quantum random numbers are not a mere curiosity but a plain necessity, for much of the world's security rests on numbers that no one can guess or predict. Ordinary machines can only fake randomness, spinning out patterns that look scattered but secretly follow a rule, and a determined adversary might in principle unwind them. A number drawn from an entangled measurement has no such rule beneath it, nothing to unwind, no thread to follow back, no seed from which a clever enemy might regrow the whole sequence. Even the universe does not know the answer before it happens. It is randomness certified by the laws of physics themselves, as unguessable as the spin of an electron that has not yet been measured and tested against Bell's inequality to prove that no hidden pattern lurks beneath. From the dreamlike uncertainty at the heart of matter comes one of the most dependable tools in all of science, a wellspring of genuine chance in a world that otherwise runs on cause and predictable effect, a small fountain of true unpredictability bubbling up from the very bottom of reality. The very emptiness of space turns out to be quietly humming with entanglement, in a way that gives the vacuum a hidden depth. What we call empty space is not truly empty in the quantum view, but a restless sea of fleeting fields, and these fields are entangled across every distance, knitting nearby regions of nothingness into a single connected fabric. Pull two imaginary boxes of vacuum apart in your mind, and the quantum description insists they were correlated, bound by faint threads of entanglement woven through the apparent void. The same restless emptiness is forever conjuring fleeting pairs of particles that flicker into being and vanish again before they can be caught, born entangled in the very act of appearing, a soft and ceaseless foam beneath the surface of nothing. This is one of the deepest and most actively studied ideas in modern physics, the notion that the smooth fabric of space itself might be sewn together out of entanglement, that the very nearness of here to there could be, at bottom, a quantum connection. The emptiness all around you, and all the dark between the stars may be the most entangled thing of all, less an absence than a soft humming presence woven through with hidden ties. In recent years, some of the boldest physicists have begun to wonder whether even gravity, the force that holds you to your bed and swings the planets round the sun, might arise from entanglement at the deepest level. There is a striking idea, still being explored, that the way space curves and bends near a heavy object could be the large-scale shadow of how quantum information is entangled beneath it. In this view, the shape of the cosmos itself is woven from countless quantum threads, and gravity is what that weaving looks like from far away, the way a smooth sheet of cloth, seen from across a room, hides the countless fibres that give it form. It is not yet proven, and wise people argue about it still with great care and no little excitement, but the mere possibility is breathtaking. Imagine that the steady pull holding you safe against the earth, the weight that settles you into your bed each night, might be in the end the same gentle connection that binds two flecks of light, the same thread followed all the way up to the scale of worlds. If it is so, then you have never once, in all your life, been anywhere but inside an embrace of entanglement. A related and equally astonishing conjecture goes by the playful shorthand of a simple equation, the claim that two entangled black holes might be the same thing as a wormhole joining them, a tunnel through the fabric of space. Two physicists named Maldacena and Susskind proposed that the mysterious connection of entanglement and the geometric idea of a bridge between distant places might be two descriptions of one underlying truth. If this is right, then to entangle two things is, in some sense, to grow a hidden thread of space between them, however faint and impossible to walk through. The spookiness Einstein feared would turn out to be the very stuff of geometry, distance and connection, revealed as two faces of a single deeper reality, two words for one underlying thing. There is a lovely irony in it, that the puzzle Einstein raised to embarrass quantum theory might find its resolution in his own theory of curved space and time, the two halves of his life's work meeting at last across the decades. These are frontier ideas, unconfirmed and hotly discussed, but they show how far the small puzzle of entanglement has reached, all the way to the architecture of the universe, all the way to the question of what space itself is made of. Entanglement also weaves quietly through the living world in ways scientists are only beginning to map. Inside the green machinery of plants, in the act of photosynthesis, the energy gathered from sunlight seems to find its way through the leaf with an efficiency that hints at quantum effects, with delicate, fleeting coherences guiding it along the best path. Some researchers suspect that birds may navigate by sensing the Earth's magnetic field through entangled pairs of particles formed in their eyes by incoming light. The leading idea points to a protein called cryptochrome, tucked into the retina, where a flash of light is thought to split a molecule into two parts, each carrying a lone electron, the two spins born entangled and ever so faintly sensitive to the direction of the planet's magnetic field. A migrating robin, in this picture, might quite literally see the field as a soft pattern laid over its vision, reading the invisible lines that guide it across continents in the dark of an autumn night. Remarkably, the delicate quantum coherence such a sense would require seems, in laboratory studies of these proteins, to last longer than chemists have managed to achieve in their own carefully built molecules, as though life had quietly solved a hard problem first. These ideas are still tender and debated, not yet settled fact, but they raise a lovely possibility that the strange connection at the heart of physics is not locked away in frozen laboratories, but stirring, faintly, in the warm green workings of life itself, in the eye of a small bird crossing a darkening sky. Consider the sheer difficulty of what the experimenters achieve and the patience it demands. To hold an entangled state, they must shield their particles from nearly everything, from heat, from light, from the faintest tremor of the building, from stray magnetic fields, from the soft jostle of air. They work in chambers pumped down to a vacuum emptier than the space between the planets, cooled to temperatures a hair above the coldest possible cold, mounted on tables that float on cushions of air to keep out the faint shiver of footsteps in a distant hallway. They shield against the magnetism of the earth, against the warmth of their own bodies, against the light of a single stray lamp, and even then the connection survives only for the briefest flickers of time. The whole enterprise is a kind of devotion, an immense and careful tenderness aimed at protecting something almost impossibly delicate, long enough to ask it a single quiet question before the world rushes back in and the answer dissolves. There is a deep tenderness in it, this guarding of so faint a flame against so vast a draught. There is a famous and gentle puzzle that helped make all of this vivid, the thought experiment of a cat that is, in a sense, both asleep and awake at once. Schrödinger imagined it to show how strange the quantum rules become when carried up to everyday size, how a single undecided particle, if linked to larger things, might seem to spread its undecidedness onto them. The cat is entangled with the particle, its fate braided to whether the particle has shifted or not, and so, on paper, it hovers between two states until someone looks. The point was never a real cat, of course, nor any cruelty to an animal, but a way of feeling the mystery in the bones, of dragging the strangeness up from the invisible realm of atoms into a picture the mind can hold. Schrödinger meant it almost as a sly provocation, a way of asking where exactly the blur of the small gives way to the solidity of the large. We now understand that decoherence answers him. A thing as large and warm as a cat touches its surroundings so constantly that it could never hover for even the faintest instant. It shows how entanglement is the bridge by which the haze of the very small could, in principle, climb up into the world of ordinary things, if only that world would hold still long enough, and why, in practice, it almost never can. Scientists have now pushed entanglement up towards sizes you could almost see, which once seemed unthinkable. They have entangled tiny mechanical drums, small membranes vibrating in unison, objects large enough to be glimpsed under a good microscope, holding them in a shared quantum state for a fleeting moment. They have linked the collective motion of trillions of atoms in two separate clouds. In one remarkable experiment, scientists at Oxford entangled two small diamonds, each about the size of a grain of rice, and sitting 15 centimeters apart on a bench at ordinary room temperature, binding the faint vibrations of one to the faint vibrations of the other. These were not invisible motes, but objects you could have picked up between two fingers, briefly sharing a single quantum state in the warm, bright air of an ordinary laboratory. Each such feat pushes the boundary between the quantum and the everyday a little further out, showing that there is no sharp wall where the strangeness stops, only a soft fading as things grow larger and warmer and harder to keep still. The dreamlike rules do not belong solely to the unimaginably small. They reach faintly toward the scale of the world you can touch, if the world is only hushed enough. The connection has even been carried into the deep cold of the open sky and held there. Beyond the satellite that rained entangled light onto distant mountaintops, experiments have sent entangled photons through long stretches of open air between mountain peaks, and down into the murk of lakes and the sea, testing how far and through what the fragile bond can travel. Each test maps the edges of the possible, charting where entanglement endures and where the noisy world finally frays it apart. Slowly a picture forms of a connection more robust than its delicacy might suggest, able to survive a journey through turbulent air and even through scattering water, provided enough care is taken at every step. Light sent through seawater is buffeted and bent and partly swallowed, and yet enough entangled photons come through to prove the bond endures, an encouraging sign for any future network that might one day reach beneath the waves. The thread is fine, easily lost to a careless hand, but it is not so easily broken as one might fear, and it reaches farther with each passing year, into places that once seemed impossibly hostile to anything so delicate. One subtle and beautiful fact is that entanglement comes in degrees, like a bond that can be drawn tight or left loose. Two particles may be only faintly entangled, sharing just a whisper of connection, or they may be entangled as completely as the rules allow, bound in what physicists call a maximally entangled state. There are even careful ways to measure exactly how much entanglement a pair holds, to put a number on the strength of the invisible thread. And there are clever procedures, with the lovely name of entanglement distillation, that can take many weakly linked pairs and concentrate their connection into fewer, more perfectly bound ones, like gathering scattered light into a single bright point, or pressing many faint sips into one strong draught. The connection is not simply present or absent, not merely a yes or a no, but a quantity, a resource that can be measured, refined, traded, and spent like any other precious thing. Physicists speak of it almost as they might speak of fuel or gold, something to be gathered and conserved and used with care, the working substance of a whole new kind of technology. It is humbling to recall that this whole towering field grew from a question nobody thought could be answered, a quarrel about the meaning of the equations that most working scientists were content to ignore. The people who pushed it forward in the lean early years were often regarded as eccentrics, chasing a philosophical will-o'-the-wisp with no practical payoff in sight. John Bell himself never lived to see the grand experiments that finally confirmed his vision, nor the Nobel Prize that honoured it. And yet from that supposedly useless puzzle has come quantum computing, unbreakable codes, the finest clocks and sensors ever made, and a deep new window onto the nature of reality. Bell pursued his question for love of understanding alone, with no thought of any payoff, and the payoff came anyway, decades later, in forms he could scarcely have imagined. There is a quiet lesson resting in that, about the worth of wondering for its own sake, about how the most impractical questions sometimes open the widest doors, about how a single curious mind, following a thread that everyone else had let drop, can change the course of human knowledge. The deeper one looks, the more entanglement seems less like an exotic special effect, and more like the ordinary grammar of the quantum world, its native and constant condition. Particles that interact become entangled almost as a matter of course, their fates quietly braiding together with every meeting. The reason we rarely notice is only that this delicate bookkeeping is swiftly spread out and hidden among the countless particles of the warm world around them, washed into the general blur. But the entanglement is always being made, everywhere, in every interaction, an endless and invisible weaving that never pauses for an instant. Every time two particles so much as brush against one another, a faint thread is tied. The universe is forever tying tiny knots between its pieces, and then forever losing track of them in the noise, scattering each fresh connection into the vast warm blur almost as soon as it forms. It is a great loom that never stops, threading connection through everything it touches, weaving and unweaving the world in the same ceaseless breath, far too quickly and too quietly for any eye to follow. A particularly mind-easing subtlety lives in the question of which measurement comes first. Suppose two entangled particles are measured at nearly the same moment in two distant places. Because of the way time itself bends in Einstein's relativity, different observers, moving differently, might genuinely disagree about which measurement happened earlier. One might say the left particle was measured first, and the right one fell into line. Another might insist it was the other way around. And yet they all see the same perfect correlation, the same matched results, no matter whose accounting of time they keep. There is no contradiction, because no actual influence travels between them, nothing that needs an order, no cause that must come before its effect. If a real signal had passed from one to the other, this disagreement about timing would tear the world apart with paradox. Because nothing passes, because the harmony was woven into the pair from the start, the differing stories cause no trouble at all. The harmony is simply there, indifferent to who measured when. The strangeness and the deep consistency of physics fit together without a seam, two truths that ought to clash resting instead in perfect peace. Physicists have a careful way of describing an entangled particle taken on its own, apart from its partner, and the description is oddly peaceful. Looked at alone, with no knowledge of its distant twin, a single entangled particle appears to be in a state of pure, featureless uncertainty, a perfect blur with no preference for any outcome. All of its definiteness, all of its character, lives not inside it, but in the relationship, in the correlation with the other. The particle by itself is, in a sense, less than half the story, holding none of the answer privately. This is one of the most quietly astonishing facts in all of physics, that two particles can together be in a perfectly definite, fully known state, while each one alone is utterly undefined. The whole is sharp and complete. The parts are a soft haze. Only the pair together carries the full truth. It is a strange and lovely thing that the meaning resides entirely in the connection, and that each particle alone is a kind of soft and waiting emptiness. The careful accounting of how much an entangled system knows about itself leads to a deep quantity called entanglement entropy, a measure of how thoroughly two parts of a system are bound. The more entangled the parts, the more this entropy grows, and physicists have found that it follows beautiful and surprising patterns. In many systems, the entanglement between a region and its surroundings depends not on the volume of the region, but on the area of the boundary around it, on the size of the surface rather than the space within. This unexpected rule, that connection is counted by surface rather than by bulk, echoes a famous principle about black holes, whose hidden capacity is likewise measured by the area of their horizon and not by the volume within. That two such different corners of physics should obey the same strange accounting feels like a clue, a hint that some single deeper law is showing its face in two places at once. From the simple idea of two linked particles unfolds a whole quiet geometry of connection, a hidden order that physicists are still working gently and with great excitement to fully read. That same idea reaches into one of the great puzzles about black holes and helps to calm it. For a long time it seemed that a black hole might swallow information forever, erasing it utterly, which would break one of the most cherished rules in physics. The threads of entanglement offer a way out. The light that slowly leaks from a black hole over unimaginable ages appears at first to be featureless, but careful reasoning suggests it is subtly entangled with everything that fell in, carrying the lost information out in scrambled, encoded form. Nothing is truly destroyed, only hidden in correlations too complex to easily read, scrambled past recognition, yet never erased. The greatest minds in physics argued over this puzzle for decades, and the slow resolution still being worked out turns again and again on the patient bookkeeping of entanglement. Entanglement in this telling is the universe's way of keeping its books balanced even at the edge of a black hole, that most ravenous of objects, ensuring that the story of what fell in is never quite, completely gone, only folded away into a code too deep for any reading. There is a kind of three-particle entanglement, gentler than the all-or-nothing GHZ state, known as the W state, and it has a quietly reassuring quality. In a W state, the connection is shared more loosely among the three, so that if one particle is lost or disturbed, the entanglement between the remaining two survives rather than vanishing entirely. It is a more forgiving arrangement, a bond that bends without breaking. This robustness makes such states precious for building quantum technologies that must endure the inevitable bumps of the real world, where perfect stillness can never quite be reached. Lose one strand of a W state, and the remaining bond merely loosens rather than snapping clean. Where the GHZ state is fragile and total, holding everything or nothing, the W state is supple and persistent, bending where the other would break. Between them they show that even the geometry of connection comes in different temperaments, some delicate, some resilient, like different kinds of knots tied for different needs, and that nature offers more than one way for things to be bound together. The threat of decoherence, of the world forever fraying these bonds, has called forth one of the cleverest ideas in all of science, quantum error correction. Since a single qubit is so easily disturbed, physicists spread the information of one protected qubit across many physical ones, entangling them so artfully that the precious state lives not in any single particle, but in the pattern shared among them. Then, if the noisy world nudges one of them astray, the disturbance can be detected and quietly undone. without ever directly reading or destroying the protected information itself. It is a way of building something sturdy out of fragile parts, of weaving a durable thread from many delicate ones, much as a rope of countless thin fibres can bear a weight that no single fibre could. No one particle holds the secret, so no one disturbance can steal it. The information lives in the pattern, and the pattern can heal. The very entanglement that the world tries to break becomes, turned to this purpose, the means of protecting the connection from the world, the disease and its own cure drawn from a single source. It is one of the most beautiful turns in the whole story, fragility itself enlisted in the service of endurance. It turns out that nature has been making entangled light, on her own, for as long as there have been stars. Deep inside the sun and every other star, in the fierce processes that make their light, photons are sometimes born in pairs that share quantum correlations. Faint entanglement is generated in countless ordinary physical processes throughout the cosmos, in the glow of hot gas, in the scattering of light off a dust grain, in the steady workings of matter everywhere, in the collisions and couplings that fill every corner of creation. Every flame, every sunrise, every flicker of starlight carries some thread of it, made and scattered in the same breath. Long before any human built a crystal to make entangled pairs on purpose, before there were eyes to see or minds to wonder, the universe was weaving these threads in the hearts of stars and the cold reaches of space. The phenomenon that took a century to understand has been a quiet, constant feature of the cosmos from the very beginning, an old and natural part of how the world is made. There is a thought experiment, sometimes called the puzzle of Wigner's friend, that gently stretches the question of measurement to its limit, and it need not trouble your rest. It imagines an observer inside a sealed laboratory making a measurement, while a second observer outside describes the whole laboratory, including the first observer, as a single entangled quantum system not yet resolved. From inside, an answer has been found. From outside, the question hangs open. The puzzle asks how both views can be true at once, and it has no settled answer, only deepening conversation among thoughtful people who have pondered it for decades without agreeing. Perhaps both descriptions are right in their own frames. Perhaps the very act of observation must be understood more subtly than anyone yet knows. You may simply let it rest as it is, unresolved and unhurried, an open and beautiful question about where the act of knowing fits into the fabric of the world. Not every mystery needs solving tonight. Some are sweeter for being left open, like a door ajar onto a dim and pleasant room, and this is one of them. Some of the most precise measurements of entanglement now use not two particles, but the joint behaviour of many, in systems carefully tuned so that the connection can be read with exquisite confidence. In these experiments, the violation of Bell's limit is so stark, so far beyond what any hidden script could produce, that the old debate is settled past any reasonable doubt thousands of times over. In the cleanest modern tests, the chance that the result could have come from ordinary hidden instructions is smaller than the chance of guessing a single grain of sand chosen from all the beaches of the earth. Each clean result is another quiet confirmation that the world is at bottom exactly as strange as the equations have always said. There is a deep steadiness in that, in knowing that this most counterintuitive feature of reality has been checked and rechecked, gently and rigorously, until it stands as one of the most secure facts there are about the nature of things. The connection has been demonstrated between particles separated not only by space, but, in a sense, across time, in experiments of great subtlety. Physicists have entangled photons that never coexisted, where the first was measured and gone before the second was even born, and yet the two show the unmistakable correlations of an entangled pair. This is achieved through the swapping of entanglement, that handing off of connection through a later measurement, which can reach backward to link particles whose lifetimes never overlapped, binding a photon long since absorbed to one only just created. It does not mean signals travel through time, nor anything that breaks the orderly flow of cause and effect. No message is sent into the past, and nothing already settled is undone. The order of events stays whole. only the description of the link reaches across moments. It means only that the bookkeeping of entanglement is stranger and more flexible than our ordinary picture of separate moments allows, a connection that does not always respect the simple, before and after we take for granted. That treats time itself with a curious and gentle freedom while never once breaking a single law. The world remains perfectly orderly, even as it quietly defies the tidy story we tell ourselves about what comes first. There is a charming counterpart to teleportation, running in the opposite direction, called superdense coding. Where teleportation uses entanglement to send a quantum state with the help of ordinary bits, superdense coding uses entanglement to pack extraordinary information into a single quantum particle. If two people share an entangled pair beforehand, one of them can send two full bits of a message by adjusting and forwarding just one particle, twice the usual cargo carried by such a small messenger. Ordinarily, a single particle, prepared one way or another, can carry only a single yes or no. But with a shared entangled pair laid down ahead of time, the same lone particle can carry twice as much, as though the prior connection had quietly enlarged the space inside it. The entanglement, prepared in advance, acts like a hidden channel that doubles the capacity. It is a small marvel of efficiency, a way of using the connection as a kind of pre-laid groundwork that lets a single particle speak more than it otherwise could, and another sign of how rich a resource entanglement truly is. The first complete scheme for unbreakable communication using these ideas was devised in 1984 and is known by the initials of its two inventors, a method for two parties to build a shared secret key by sending single particles of light, one at a time, each carrying a fragile bit that any eavesdropper would inevitably spoil by looking. A few years later, in 1991, a more elegant version proposed by the physicist Arthur Eckert used entanglement itself as the foundation, drawing its security directly from the violation of Bell's inequality. The logic is exquisite. If the two parties test their entangled particles and find the telltale quantum correlations intact, they know with certainty that no eavesdropper has touched them, for any interference would have spoiled the delicate connection. The deepest mystery of quantum physics, the spookiness Einstein distrusted, becomes the very guarantee that a secret is safe. An ordinary code, however clever, rests on a problem merely too hard to solve quickly, and a hard problem may yield to a faster machine some distant day. A code built on entanglement rests on the laws of nature themselves, which no machine, however mighty, can ever overturn. The strangeness is not a danger, but a lock that cannot be picked, a seal whose security is underwritten by the universe. To rule out one last subtle doubt that some unknown influence might be quietly steering the choices made in a Bell test, physicists devised experiments of remarkable poetry. In one, called the Cosmic Bell Test, the decisions of what to measure were determined by the ancient light of distant quasars, light that had travelled across billions of years of space to reach the detectors. Since that light left its sources long before the experiment was even imagined, indeed long before the Sun and the Earth had even formed, no hidden conspiracy in the laboratory could have arranged the choices in advance. For any secret coordination to have crept in, it would have had to be set in motion billions of years ago in the youth of the universe itself, an absurdity too vast to credit. And still the quantum correlations held. The universe was, in effect, asked to confirm its own strangeness using starlight older than the Earth, and it answered yes. There is something deeply moving in that, in using the oldest light in the sky to settle the newest question about reality. In another lovely effort called the Big Bell Test, the choices in a worldwide set of experiments were made not by machines, but by tens of thousands of ordinary people, scattered across the globe, tapping freely on their phones to feed a stream of human-chosen decisions into the laboratories. The idea was to close the faint possibility that the choices were secretly predetermined, by drawing them instead from the unpredictable whims of free human will. People playing a simple game, each tap a tiny act of choice, together became part of a grand test of the foundations of physics. On a single day in late 2016, This gathered crowd fed millions upon millions of free human choices into a dozen laboratories scattered across 5 continents, and the experiments ran on the steady stream of human whim. And once again, the entangled particles defied the old limit, in laboratory after laboratory, all around the turning world. It was a rare and beautiful thing, a moment when the curiosity of a crowd of strangers was woven directly into one of the deepest experiments ever performed, the free will of ordinary people stitched into the very fabric of a question about reality. Physicists have developed delicate tools called entanglement witnesses, which can detect the presence of entanglement in a system without needing to fully unravel its delicate state. A witness is a single, carefully chosen measurement whose result will exceed a certain value only if entanglement is truly present. A kind of faithful sentinel that says yes, the connection is here, without disturbing more than it must. This matters because fully mapping an entangled state can require an enormous number of measurements, growing so swiftly with each added particle that for a large state the full accounting could take longer than any human lifetime. A witness, by contrast, can confirm the connection with just one well-aimed look. It is the difference between counting every leaf on a tree and simply noticing that the tree is green. With such tools, scientists can verify that their fragile creations are genuinely entangled, swiftly and with a light touch, catching the presence of the bond before it has time to fade. It is a quiet art, this knowing without disturbing, a way of asking the gentlest possible question and trusting the answer. The largest entangled states ever assembled now stretch across remarkable numbers of particles, knit together in laboratories with painstaking care. Scientists have entangled dozens of photons at once, and on certain specialized quantum machines, the number of entangled qubits has climbed well past 1,000, each one bound into a single shared quantum object. To create and verify such states is a feat of staggering delicacy, for the difficulty of holding the connection grows swiftly with every particle added. Yet the numbers keep rising year by year as the art improves, the records falling one after another as new laboratories and new methods come of age. Each added particle roughly doubles the difficulty, and so every step forward is harder one than the last, a steeper climb at every stage. Each new record is a quiet milestone, a sign that the dreamlike connection once thought impossible to even test is now something we can build deliberately, on purpose, at scales that would have seemed pure fantasy only a generation ago. What was once a delicate accident, glimpsed and lost, has become something we can summon and hold, knit larger and larger by patient hands. It is worth pausing on the sheer smallness of the things being connected to feel the wonder of it fully. A photon has no mass at all, and is gone the instant it touches anything. An electron is so small that billions could rest within the width of a single hair. An atom is mostly empty space, a tiny dense core wrapped in a haze of even tinier electrons. If an atom were swelled to the size of a cathedral, its heart would be no larger than a grain of salt at the very centre. And it is between these almost unimaginably small things, across the vast inner emptiness and the great outer distances alike, that the connection is forged, threads of entanglement strung between motes too small to ever see. There is a strange tenderness in the picture, the universe reaching down to its very finest grain and tying it, gently, to another grain just as fine, across whatever distance lies between, with a faithfulness that the largest things can only envy. The smallest pieces of the world, it turns out, are capable of the most far-reaching bonds. The mathematics that describes an entangled pair is, in its own way, startlingly simple and clean, a brief expression that nonetheless contains the whole mystery. It cannot be split into a separate description for each particle, no matter how one tries, and that very impossibility of separating it is the mathematical fingerprint of entanglement. A state that can be pulled cleanly apart into 2 independent stories is not entangled. A state that resists every such pulling, that insists on being written as one indivisible whole, is. This unsplittable quality is what physicists actually mean by the word beneath all the poetry. There is a deep beauty in how plain the underlying truth turns out to be once it is stripped of its mystery. It is not that some force reaches between the particles, not that any influence travels or any signal flies. It is simply that the truest description of them is one and cannot be cut in two. The connection is not a thing added to the particles, but a fact about how they must be described together. Entanglement is, at heart, the refusal of a description to come apart, the insistence of two things on being written as one, and from that simple refusal flows every wonder in this long, quiet story. Among the gentler surprises is that entanglement can be created between particles by the simple act of measuring them together in the right way, even if they began as strangers. Bring two unrelated particles into a joint measurement that asks about them as a pair rather than separately, and they can emerge entangled, bound by the act of being looked at as one. It is as though the very questions we ask of the world can stitch its pieces together, that observation is not only a taking of information but sometimes a making of connection, not only a reading of the page but a writing upon it. This is the principle behind entanglement swapping, behind the joining of strangers into a single bond, behind much of what makes a quantum network even thinkable. There is something quietly profound in that. The thought that to consider two things as a single whole, in the precise language of quantum measurement, can be enough to truly join them, weaving a thread where none had been before. To look, in the right way, is to bind. The act of knowing and the act of connecting turn out down here to be very nearly the same. The connection has been carried, by now, across nearly every kind of barrier the world can offer. Entangled photons have been sent through the air between distant rooftops, down long cables beneath city streets, through the turbulent atmosphere, from orbit to the ground, and through stretches of water. Each new medium once seemed likely to scramble the fragile bond beyond repair, and each in turn has been crossed. The picture that emerges is of a connection more travel-worthy than its delicacy suggests, capable of surviving a real journey through a messy world, provided the journey is made with enough care and the noise kept low enough. Each crossing once thought impossible has, with patience, been made possible. The thread is fine as gossamer, easily broken by a careless touch, yet it has now reached across cities, through the cold water of the deep, and down from the very edge of space, farther in each passing year than the year before. What began on a single tabletop, two photons separated by the width of a room, now spans the gap between a satellite and a mountaintop, and the horizon of the possible keeps quietly receding. There is a deep revolution underway in how we understand information itself, and entanglement sits at its centre. In the ordinary world, information is a simple thing, a string of yes and no, here and there, on and off. The quantum world reveals a richer kind, one in which the information is not held in the pieces but distributed across the whole, smeared through the correlations between particles in a way that has no ordinary counterpart. Two entangled qubits can carry more than the sum of what each could hold alone, because part of the information lives in the relationship between them. This has forced a complete rethinking of what it even means to store, send, and process knowledge, opening a new science of information built not on bits in boxes but on threads woven between them. Whole new measures and laws have grown up to describe this richer kind of information, a quiet mathematics of connection that did not exist a few generations ago. The discovery has been as much philosophical as practical, a new way of seeing what knowledge itself truly is and where it can live. Information, it turns out, is not only a thing held in separate places, but also something that can dwell in the relationships between them, in the very pattern of how things are bound. Picture the difference between describing two ordinary objects and describing an entangled pair, and the strangeness comes clear. To describe two pebbles, you simply describe each one and set the description side by side, two separate accounts that together tell the whole story. But for an entangled pair, no such pair of separate accounts can ever capture the truth, however carefully you write them. There will always be something left out, a correlation that lives only in the joint description, in the two taken together as one. This is not a failure of language or cleverness, not a gap we might one day close with a better notebook. It is a deep fact about the world itself. Some things in nature genuinely cannot be reduced to a list of their parts, however complete that list. The whole carries truths that the pieces, described separately, can never hold, no matter how minutely each is examined. Entanglement is the clearest example ever found, the sharpest proof that the universe is, in places, more than the sum of what it is made of, and that wholeness can be a fundamental thing rather than a mere assembly of separate bits. The patient work of building quantum machines has revealed just how precious and rare a long-lived entangled state truly is. In the best laboratories, with the finest shielding and the deepest cold, scientists measure how long they can hold a qubit before the world disturbs it, a span called the coherence time, and they celebrate every small gain. Where once such states survived for only the faintest flicker, careful engineering has stretched their lives to seconds, even minutes in certain special systems, and in a few rare and beautiful cases, with atoms held just so. A single quantum memory has been coaxed to hold its delicate state for hours, an eternity by the standards of the very small. Each improvement is hard-won, the fruit of countless small refinements, better materials, colder chambers, cleverer designs, every gain measured in fractions of a second clawed back from the encroaching noise. The whole field advances by learning slowly and tenderly how to keep a fragile connection alive a little longer in a universe forever trying to smooth it away. It is a kind of patient gardening, this tending of the quantum, a long and gentle labour against the steady pull of forgetting. It is a striking thought that the same effect makes two distant things behave as one, and also makes a quantum computer powerful, for these are, at heart, the same phenomenon wearing different clothes. The spookiness that troubled Einstein, the matched coins across the galaxy, the unbreakable codes, the teleported states, the dizzying promise of quantum computation, all of it springs from a single source, the way quantum particles can share one indivisible state. To understand entanglement is to hold a key that unlocks a whole family of marvels at once. Each of these wonders, so different on the surface, the locked message, the relocated state, the blossoming computation, the steadier clock, perhaps the curve of space itself traces back to that one root, that two things can share a single indivisible description. They are not separate discoveries, but one discovery wearing many faces. There is an elegance in that unity, a sense that nature is doing one deep thing in many guises, and that the more we learn, the more these scattered wonders reveal themselves as facets of a single, simple, astonishing truth about how the world is woven. It is the kind of unity that physicists treasure most, a great many puzzles dissolving into one quiet answer. Some researchers have explored whether entanglement might play a role in the warm, wet workings of the brain, though this remains firmly in the realm of the speculative and unproven. A few bold thinkers have wondered whether quantum effects could matter for how the mind works, though most scientists are skeptical, for the brain seems far too warm and busy to hold such delicate states. What is more firmly established is that quantum sensing built on entanglement may one day map the brain's faint magnetic whispers with unprecedented clarity, reading the soft electrical music of thought from outside the skull without a single touch. Already there are quantum-enhanced detectors gentle and keen enough to sense the faint magnetic flicker of a beating heart or the slow currents of the brain, signals so soft they are nearly drowned in the noise of the world. Whether or not the mind itself runs on quantum threads, and most evidence suggests it does not, the tools born from entanglement are beginning to reveal its workings more gently and more clearly than ever before, turning the strangeness of the small toward the oldest mystery of all, the quiet machinery of thought and feeling that makes you who you are. The very act of confirming entanglement across great distances has become a kind of art form, requiring clocks synchronized to billionths of a second so that the matched measurements can be properly compared. When entangled photons are sent to stations far apart, the scientists must know, with extraordinary precision, exactly when each measurement occurred, so that they may later lay the results side by side and see the hidden harmony. This demands timekeeping of a delicacy that itself pushes the limits of technology, atomic clocks ticking in perfect step across the miles, their rhythms locked together to within billionths of a second. A mismatch of even that tiny span could blur the correlation beyond recognition, scrambling the harmony into apparent noise. The whole enterprise is a marvel of coordination, a vast and careful choreography stretched across the landscape, all in the service of catching just once the gentle correlation between two particles born together and flung apart. The precision required is itself a clear testament to how seriously the strangeness is taken, how much patient labour goes into hearing a whisper that lasts less than the blink of an eye. There is a deep principle, glimpsed but not yet fully understood, that entanglement may be the thread from which the smooth fabric of space-time is sewn. In certain elegant theories, the geometry of space, the very sense in which one place is near another, emerges from the pattern of entanglement among the underlying quantum pieces. Cut the entanglement between two regions in these models, and the space between them comes apart, the smooth continuity dissolving into disconnection. Restore the entanglement, and the geometry knits back together. In this view, the reason you can reach across a room and touch the far wall, the reason there is a smooth and continuous space to move through at all, is that the underlying quantum pieces are richly entangled, their connections summing into the seamless expanse you take for granted. If this picture is right, and it remains a frontier still being explored, then the apparent solidity and nearness of the world around you is woven, at the deepest level, from the same gentle correlations that bind two flecks of light. Nearness itself would be a kind of entanglement, the closeness of here to there a quantum thread, and the gentle space that holds you tonight a vast and silent weave. The experiments that probe entanglement are often beautiful simply to behold, gleaming with optical precision. Heavy steel tables rest on isolating supports, mounted with mirrors and lenses and crystals arranged in intricate paths, while threads of laser light trace invisible journeys through the careful geometry. In other setups, single ions hover in the heart of electromagnetic traps, glowing faintly when struck by light, suspended in a vacuum like stars held in tiny cradles. In still others, superconducting circuits chill in their golden chambers, humming with currents that flow forever without resistance, looping endlessly with no loss at all. Each apparatus is a kind of sculpture devoted to a single delicate purpose, to coax two pieces of the world into sharing one state, and to read that sharing before it fades. Whole teams of people may spend years building and tuning a single one of these instruments, aligning each mirror to a hair's breadth, hunting down every stray source of warmth and tremor. There is an austere beauty in these machines, a sense of human care made visible, of patience turned into glass and gold and light, of a deep and shared devotion to catching one of nature's faintest and most fleeting truths. It bears repeating for the comfort it brings that nothing in all of this lets information outrun light, and the universe remains as orderly as it has always been. However instantly the entangled particles seem to coordinate, no observer can use them to send a message faster than a beam of light could carry it, and no causes ever leap ahead of their effects. The randomness of each individual outcome is a perfect and unbreakable seal, ensuring that the connection, for all its wonder, can never be turned into a tool for breaking the cosmic order. Many people, on first hearing of entanglement, fear it must open some door to paradox, some way to send a message into the past or outrun a beam of light. It does not, and it cannot, and the reason is woven into the very heart of how it works. The strangeness lives entirely within the rules. There is no chaos here, no threat, no crack through which disorder might pour, only a deep and lawful marvel, a world stranger than anyone imagined, yet every bit as consistent, as dependable, as safe as the ground beneath you, as steady as the slow rhythm of your own breath. Across the whole sweep of this story runs a single, gentle thread of meaning, that the world is far less separate than it appears. The objects around you seem to sit alone, each in its own place, divided by the empty space between. But beneath that appearance, at the finest grain of reality, things are woven together in ways that pay no heed to distance, bound by correlations that span any gap. The separateness we see is, in a sense, the surface, and the connectedness is the depth. This is not mysticism but careful physics, confirmed in laboratory after laboratory, checked and rechecked by skeptical minds who tried their hardest to find another answer and could not. And there is a quiet solace in it, a sense that the universe is, at its root, more of a single fabric than a scattering of lonely parts, a whole that only looks divided to eyes too large and too warm to see the threads. The loneliness of separate things is real enough at the scale where you live, and yet beneath it runs this older, deeper truth that everything sprang from one connected source and remains, in its finest grain, bound together still. Consider how the discovery has rippled outward into the wider world, far beyond the quiet laboratories where it began. Governments and companies across the globe now pour vast effort into quantum technologies, racing to build the machines and networks that entanglement makes possible. Nations are laying experimental quantum links between their cities, threading specially prepared fibres beneath busy streets and along railway lines, launching satellites to carry the connection across continents, and training a new generation of scientists in its delicate art. Cities in Europe and Asia have already been joined by trial quantum networks, faint threads of unbreakable connection running quietly beneath the ordinary hum of daily life. What began as one physicist's lonely insight, scribbled in the margins of an old dispute about what the equations truly meant, dismissed for decades as a question with no practical use, has grown into a global endeavour employing thousands of minds and vast sums of patient investment. There is something quietly stirring in watching an idea travel that far, from a thought experiment about coins in envelopes to a worldwide effort to weave the strangest thread in physics into the fabric of ordinary life, all within a single human lifetime. One of the subtlest and most reassuring truths is that entanglement by itself can never be felt or detected from a single side. If someone far away were to entangle a particle with one resting beside you, you would notice nothing whatsoever. Your particle would behave exactly as before, its measurements scattering randomly as they always had, betraying no hint of its distant partner. Only by gathering both sets of results and comparing them after the fact by ordinary means could the connection ever be revealed. This means entanglement can never reach out and disturb you, never tug at your world without your knowledge, never announce its presence by any local sign. Right now, this very moment, particles within your body may be faintly entangled with particles far across the room, or across the city or beyond, and you would feel nothing, notice nothing, lose nothing. The bonds touch you without touching you, present yet utterly gentle. It is a connection that announces itself only to those who already hold both ends and choose to look. There is a deep privacy in that, a sense that the threads, however vast their reach, are gentle and unintrusive, touching nothing they are not invited to touch. The history of the idea is dotted with moments of quiet courage, of people who pursued the question when it was unfashionable to do so. In the lean decades when entanglement was dismissed as mere philosophy, a handful of physicists kept the flame, running careful experiments that their colleagues thought pointless, refining the questions that no one believed could be answered. They worked often without recognition, sometimes against the mild scorn of their peers, told that they were wasting their talents on a question that could never be answered and would never matter. They were sustained only by the conviction that the puzzle mattered, that the meaning of the equations was worth chasing for its own sake. It is largely thanks to their stubborn devotion, their willingness to be thought foolish, that the field exists at all. There is a lesson resting softly in that history, about the value of taking strange questions seriously, about how the deepest practical fruits, the codes and computers and clocks, sometimes grow from the most impractical seeming roots, tended patiently by those willing to wonder when wondering was out of fashion. It is humbling to realize how recently all of this became real, how young this knowledge truly is. The first crude tests of Bell's idea came barely 50 years ago. The loophole-free experiments that settled the matter beyond doubt arrived only in the last decade or so. The satellite that carried entanglement from space went up within recent memory. The largest quantum machines were built just years ago, and grow more capable by the season. You're living right now through the early morning of this entire science, in the very years when humanity is first learning to make, hold, and use the strangest connection in nature. The people who ran the decisive experiments are mostly still alive, still working, still pushing the frontier outward, season by season. The whole story, from Bell's quiet insight to the satellites and the 1,000-qubit machines, has unfolded within a single human lifetime, faster than almost anyone dared hope. A child born today may grow up in a world where quantum networks are as ordinary as telephones, where unbreakable connection is simply part of the furniture of life, never knowing that the thread beneath them was, within living memory, thought to be impossible even to test, a mere philosopher's daydream. There is a particular beauty in the fact that entanglement reveals a limit to what can ever be known about a single particle, and turns that limit into a gift. Because each entangled particle holds none of the answer privately, keeping it secret entirely in the shared correlation, no measurement of one alone can ever pry loose the full truth. This is the same principle that makes quantum codes unbreakable, that keeps the random numbers truly random, that protects information spread across many qubits. In the old picture of the world, every fact was there to be read by anyone clever and patient enough to look closely. The quantum world is gentler and more private than that. Some truths exist only in the joining of things and simply cannot be extracted from the pieces alone, no matter how hard one tries. The world's refusal to let a single particle be fully known, taken in isolation, is not a wall against understanding but the foundation of a whole new kind of security and trust. What looks at first like a boundary on knowledge turns out to be the very thing that lets us build connections no eavesdropper can ever quietly breach, a privacy written into the bones of reality. Some of the most delicate experiments now entangle not just pairs or trios, but carefully shaped clusters of particles, arranged in patterns designed for computing. In one approach, called measurement-based quantum computing, a large entangled cluster is prepared all at once, and then the computation proceeds simply by measuring the particles one by one in a chosen order, the answer emerging from the pattern of measurements. It is a strange inversion of the ordinary picture, in which the computing happens not by pushing the particles through operations, but by reading them out in just the right sequence, each measurement guided by the ones before it, letting the pre-woven entanglement do the work. The whole calculation lives in a sense in the initial weave of connection, waiting to be drawn out by the act of looking. The richness was placed there at the start, in the great shared web of entangled particles, and the computation is simply the patient, ordered drawing of it forth. It is computing as a kind of careful unravelling, the answer hidden in the threads from the start, coaxed gently into the open one gentle measurement at a time. The phenomenon has even reshaped how physicists think about the arrow of time, about why the past feels so different from the future. There is a deep idea that the relentless growth of entanglement, as particles interact and spread their correlations ever wider through the world, may be part of why time seems to flow in one direction. As the universe ages, more and more of its pieces become subtly entangled with one another, the threads multiplying and spreading, the information dispersing into ever larger webs from which it never quite returns. A drop of ink in clear water spreads and never gathers itself back. In much the same way, entanglement spreads outward through the world and is never seen to reverse. This steady, one-way weaving may be bound up with the very sense of time's passage, with the reason a broken cup never leaps back together, with the reason you remember the past but not the future. It is a profound and still debated thought that the flow of time itself and the spreading of entanglement through the cosmos might be, at the deepest level, two aspects of one great unfolding, time and connection ripening together as the universe grows older. Picture the universe in its first moments, unimaginably hot and dense, every particle crowded against every other. In that primordial closeness, everything was interacting with everything, and so, by the rules of the quantum world, everything was becoming entangled with everything else. Faint threads of correlation were woven across the whole of creation in those first instants, before the universe expanded and cooled, and the threads were scattered and hidden in the growing noise. In a sense, every particle in existence may carry the ghost of an ancient entanglement, a whisper of connection reaching back to the shared origin of all things, threads spun in the first fraction of a second and never wholly cut. The atoms in your hand, the light from the farthest galaxy, the cold dust drifting between the stars, all of it descends from that one blazing closeness, when there was no distance yet to separate anything from anything else. The cosmos may be, at its root, a single entangled whole, descended from one connected beginning, its apparent separateness only the long unwinding of a unity that was there at the very start. The distances came later, the connection came first. There is a quiet wisdom in how physicists have learned to treat entanglement not as a paradox to be resolved, but as a feature to be used and understood. The early decades were spent agonizing over what it could possibly mean, how nature could behave so strangely. The modern approach is gentler and more fruitful, accepting that this is simply how the world is, and asking instead what wonders can be built upon it. The shift mirrors a kind of maturing, a moving from anxious questioning toward calm acceptance and creative use. The strangeness has not been explained away, for it remains as deep as ever, but it has been befriended, woven into the tools and the understanding of a new age, no longer a source of unease but of possibility. Einstein wanted the spookiness gone, wanted the world to be simple and separable and sensible underneath. The world declined, and the generations that came after made their peace with that refusal, and in making peace with it, found riches Einstein never dreamed of. There is a model for living in that, perhaps, in learning to rest easy with a mystery rather than wrestling it forever, in letting a strange truth simply be true and building something beautiful upon it. The threads of entanglement once made leave a kind of permanent mark on the structure of the world, even after the particles have parted ways. Though decoherence scatters the connection into the surrounding environment, the correlations are not truly destroyed, only spread so thinly across so many particles that they can no longer be gathered back. In principle, the information persists, woven into the vast tapestry of the world, never quite erased, only hidden beyond any practical reach, scattered too widely for any hand to gather it back. This is part of why physicists believe that information is never truly lost in the universe, that the books always balance in the end, that nothing real is ever utterly forgotten by the cosmos that holds it. A whisper spoken into a great hall does not vanish, but spreads into countless faint echoes. In the same way, every entanglement disperses rather than dies. Every entanglement ever made has left its faint and indelible trace, threaded into the cosmos, an enduring record of every connection that has ever formed since the beginning of time, held forever, even if never to be read again. Nothing is lost, it is only spread too thin to find. There is a beautiful symmetry in how entanglement connects the largest questions to the smallest things, binding cosmology to the behaviour of a single photon. The same phenomenon that lets a satellite share a secret with the ground may also underlie the structure of space-time and the fate of information in black holes. The study of two linked particles in a quiet laboratory turns out to touch the deepest questions about the origin and architecture of the universe. Few ideas in all of science reach so far across the scales of nature, from the unimaginably small to the cosmic, from a flicker of light to the shape of reality itself, from a single afternoon in a laboratory to the first instant of the universe. To follow the thread of entanglement is to be led gently from the most practical of technologies to the most profound of mysteries, all along a single unbroken line of careful thought, never once leaving the firm ground of tested physics. It begins with a humble fact about two particles, and it ends, if it ends at all, somewhere near the deepest question there is, the question of why there is a connected world here at all, and what holds it so faithfully together. Among the most heartening developments is how entanglement is being woven into the everyday tools of science, quietly improving instruments far beyond the world of physics. In medicine, quantum-enhanced sensors promise sharper images of the body's inner workings, reading faint signals that ordinary devices would miss. In navigation, entanglement-sharpened clocks and sensors may one day guide a traveller without relying on satellites at all, by feeling the subtle tug of gravity and motion with exquisite precision. In the study of materials, entangled probes can map the hidden structure of substances atom by atom, revealing the secret architecture of crystals and molecules. In imaging, pairs of entangled photons can form pictures using light so faint it would scarcely register, gentle enough not to harm the delicate thing being looked at. The strangest idea in physics is slowly becoming a steady workhorse, lending its delicate power to 100 practical ends, making the unseen visible across every field it touches, gently expanding what human senses can reach. What was once the subject of fierce philosophical argument now hums away inside ordinary instruments, helping doctors and chemists and engineers see a little farther into the fine grain of the world. It is worth dwelling on the perfect democracy of quantum randomness, the way it touches every entangled measurement with the same untraceable chance. Whoever reads one particle of a linked pair, the answer that arrives is not influenced by who they are, where they stand, how rich or clever or powerful they might be. The universe offers the same pure, unguessable randomness to everyone, drawn from the same bottomless well. There is no privilege at the quantum level, no way to peek behind the curtain, no special knowledge that could tip the odds. The wisest physicist alive and a child seeing the apparatus for the first time stand on exactly equal ground before that single flip, both equally unable to know what will come. In a world so full of hidden advantages and unequal knowledge, there is something quietly just in this, that the deepest randomness in nature is utterly impartial, the same for all, a fairness woven into the very foundation of things, asking nothing and favouring no one. Whatever else may be unequal in the world above, down here at the root, the dice are perfectly, beautifully fair. The phenomenon has inspired not only science, but a slow shift in how thoughtful people picture the world itself. Where the old vision imagined reality as a vast machine of separate parts, each pushing on its neighbours like gears in a clock, the new picture is softer and more woven, a reality in which connection runs deeper than separation, in which the whole is more fundamental than the pieces. This is not a vague feeling, but a conclusion drawn from the hardest of evidence, from experiments repeated thousands of times by people who began as skeptics. The universe is more like a single seamless fabric than a heap of disconnected stones, more a woven cloth than a scattering of pebbles. The old mechanical vision of separate parts knocking against one another in an indifferent void gives way to something warmer and more whole. And there is a comfort in carrying that picture with you, in knowing that beneath the apparent loneliness of separate things runs a deep and constant connectedness, tested and confirmed, woven through everything that is, including you, lying here in the dark, more bound to the world than you ever knew. As this long, quiet journey nears its end, there is one last truth to rest within, perhaps the gentlest of all. The connection that binds two entangled particles asks nothing of them, demands no effort, requires no work to maintain. It simply is, a relationship woven into their shared nature, holding faithfully across any distance for as long as the world leaves it undisturbed. The particles do not strive to stay connected. They do not labour to keep faith across the miles. The bond is effortless, a part of what they are rather than something they must do, as natural to them as falling is to a stone. There is no work in it anywhere, no straining, no holding tight. And there is a soft lesson resting in that for you, here, now, sinking deeper into the warmth that holds you, letting every muscle give up its grip. The deepest connections, it turns out, are not the ones held together by effort, but the ones woven so completely into the nature of things that they simply endure, asking nothing, holding on without holding at all. And here, at the end, is the final wonder, the one to carry down with you into sleep. Every particle that makes up your body was forged in the hearts of ancient stars, scattered across space when those stars died, and gathered together again to form the earth and the air and you. In that shared and tangled origin, in the unimaginable closeness of the early universe and the long mingling of matter ever since, the atoms that are now you have brushed against, interacted with, and been faintly entangled with countless others, threads spun and scattered across billions of years. You're not a separate thing set down in an empty world. You're woven into it, descended from the same connected beginning as the farthest star, made of the same stuff, bound by the same deep rules. The connectedness that physics has found at the root of reality is not somewhere far away. It runs through you, and always has, and always will. You are a part of the single great fabric, resting now within it, held by it, at home in it completely. So let the mind grow still. There is nothing left to follow, nothing left to hold. The hidden world of the very small will go on weaving its quiet threads whether you watch or not, asking nothing of you, needing nothing from you. You may set every thought down now, the coins in their envelopes, the light born twinned in the crystal, the satellite raining connection from the sky, the threads woven through the empty space and through the stars and through you. Let them all drift away into the warm dark, settling somewhere soft, most of them passing through and gone, a few perhaps staying dim and gentle by morning. It does not matter which. There is nothing to keep. The body is heavy now, sinking into the place that holds you. The breath moves on its own, slow and deep, asking for nothing. Whatever the day has held, you may lay it down here, in the dark, among the quiet wonders, and let it go. And if you're still here, drifting at the edge of sleep, another quiet journey is already waiting for you on the screen, ready whenever you are, or never at all. There is no need to choose. There is no need to do anything. You're connected to everything, and you always have been. The world is woven whole, and you are woven into it, and nothing can untie that thread. Rest now. Let the dark be soft around you. Let the warmth hold you down into sleep. You have wandered far tonight, all the way down to the smallest grain of the world, and all the way out to the edge of the stars, and now you are home again, here in the quiet, in the dark, in the warmth. There is nothing more to know, there is nothing more to do, and now 101 wonders are resting with you. Sleep now. Good night.